Good day to everybody. As Lydia mentioned, my name's Ted Smith. I'm the field applications engineer for monolithic power sensor products, which is all magnetic-based sensing, position sensing, and current sensing. Today, we're going to be focusing on the position sensing part. And as the title suggests, we're going to be talking about the fact that rare earth materials are becoming more and more difficult to get a hold of due to certain export restrictions and other factors. Who would have ever guessed that something called a rare earth element would be difficult to obtain? But let's start with the source of the issue, which is what are the rare earth elements? They're basically, with a couple of exceptions up here, yttrium, these are the little 2-bar pull down, the starred version of the periodic table, basically, where we pull down and have a double long bar. The top row of that is essentially the rare earth elements. And we can further break them down by light rare earth elements and heavy rare earth elements. You'll notice when it comes to magnetics, some of the more important ones are neodymium, samarium for samarium cobalt, and then potentially unexpectedly, you may not know, but terbidium and deuterium and a few of these heavy rare earth elements are actually used quite commonly in neodymium magnets to stabilize and improve the characteristics, especially at higher temperatures. And so we have, along with the two light elements, a bunch of these heavy elements that aren't necessarily, you don't see them in the name of the magnet, but are often used to dope up the magnets to make the characteristics desirable. These are the kind of, well, I show 5, but let's call them 4 most commonly used types of target magnets. I say 4 because I kind of consider the injection molded and compression bonded neo as really a single thing. The only difference is the method of manufacturing, but if you look, you can see that the characteristics are almost identical for both of these types of what we can just call plastic neodymium. These are arranged in order from lowest BR, or remnant field, which is a very, very important factor when it comes to choosing a target magnet for position sensing. The higher the remnant field, the higher the field you'll have at the sensor for a given air gap. And you can see that we have ceramic or ferrite at the low end of that, and Simcoe and sintered neodymium at the high end of that. In general, in terms of restrictions, ferrite, there's absolutely no restriction whatsoever. You can get a hold of ferrite. It's very easy to get a hold of. The only issue that we have is that it's got a pretty low remnant field. The two that are becoming increasingly difficult to get a hold of are samarium cobalt, which right now almost nobody's able to use, and the sintered neodymium. Sintered neodymium, the neodymium itself is not necessarily restricted. You can get an export license for it, but the materials that are used, the heavy rare earths that are used to dope it up so that it can attain this high maximum temperature, are restricted, and so you can only get the lower grades of this sintered neodymium. The plastic neodymium, generally not an issue to get a hold of, and so what we're going to see is that if we want the really high BRs, the really high remnant fields, we're gonna run into some issues. And so the thrust of this presentation is essentially how are we going to be able to deal with having lower BR in our magnet? What can we do to make sure that our design is still viable, even though that we can't get a hold of the high remnant field magnets? I'm going to talk just one more slide about the sintered neodymium, because there are, I mentioned, various grades. The grades of neodymium have to do with this number, and that's the maximum energy product. It correlates directly with the remnant field. And so normally you have no problem getting away with or getting a hold of these N42s, N48s, the high remnant field. The problem is that they'll only work up to about 80 degrees Celsius. So if you need something that's going to be in an industrial environment or an automotive environment, you go up to 150 and beyond, you need one of these high temperature grades, which is MHSHU. It's medium high, super high, ultra high, extra high, and advanced high temperature grades. Those we cannot get a hold of, because in order to get those high grades, we have to dope the material with heavy rare earth elements, which are export restricted. And so these are very, very difficult to get a hold of right now. And so if you need to go to 150 degrees, you really have no choice but to limit the grade and limit the remnant field of your magnet. I'm going to go through this one relatively quickly because I went over time on my previous presentation. Learning how to read this so-called demagnetization curve of a magnet is something that's out of the scope of this presentation, but there are two important things. One is, what is the remnant field here? You can see this is about a 1.4 Tesla. This is an N48SH. Used to be a very, very common material that we would use in target magnets, and now difficult to get a hold of. And so because we can't get a hold of the N48SH, we have to go to just standard N48, or maybe we go down to like an N35SH, which we can get a hold of. And what's going to happen in the N35SH is these curves are all going to come lower, lower, lower. So you're only going to get about 1 Tesla or 1.1 Tesla of remnant field to be able to keep your high temperature operating. Okay, so that being said, what we're going to talk about is how can we adjust our design so that we can use a lower BR, and again, that's the remnant magnetic field, a lower BR magnet, and still get the resolution and meet all the requirements that we need of our design. And as a starting point for how that's going to work, we're going to talk about what a magnetic position sensor actually, quote unquote, sees. So a magnetic position sensor really only sees one thing, and that is the direction of the magnetic field and the amplitude of the magnetic field at a given point in space. So we're going to model a magnetic position sensor as a point field sensor. And most of the sensors that we have or that you're going to use as in a magnetic angle sensing application are going to take that field at the point. So here's a field. I used a force vector. This should actually be B field. But anyway, this is flux density. So I've got a vector of flux density that's pointing in some arbitrary direction. We can break it down into its 3 orthogonal components. So it's got a Fy, Fx, and Fz, or By, Bx, and Bz, if we want to call it that. And the sensor, most sensors sense 2 components. So they sense in a single plane. So for instance, if our sensor was laying on the XY plane, it would only sense the Fy and the Fx, and it would ignore the Fz. And that's how most sensors work. It'll sense up to 2 components. Some sensors will sense 3 components. Some sensors will only sense 1 component. But in general, most sense 2. And the way that works, an intuitive way to look at that is, let's take a magnet here. In magnets in general, the magnetic field exits the North Pole and eventually circles back around to the South Pole. This is what it looks like. Here's a disk magnet with the North Pole on the right side. You can see the field kind of circles around, and we're going to place a magnetic angle sensor in space here on the right side of this magnet. If I place the sensor right here, the sensitive part is directly in the center, and it's important to know where the sensitive part of a position sensor is. For MPS sensors, almost without exception, the sensitive area, the point that we're sensing the field in, is going to be in the direct center of the package in all 3 axes. So a typical package is like a QFN, as you can see up here, 3 by 3 by 1 millimeter. The sensitive point will be at 1.5 by 1.5 by 0.5 millimeters. And if I place this sensor right here, It's going to ignore any component of the field that comes in and out of the screen, which is fine. That's we've got it. We're showing the projection in the 2D space here, and it sees the field pointing directly to the right. If I rotate the magnet 45, I think I'm going to rotate the magnet. Let's go. There we go. If I rotate the magnet 45 degrees, then we now have from this point here, I've got an arrow that points basically to the corner of the IC. So it's a 45-degree angle, and that's what we're seeing and what we're reporting. And that makes sense because we rotated the magnet 45 degrees, and now I'm getting a 45-degree output. Rotated another 45 degrees, I get a 90-degree output, and so on. So that's what a sensor, quote unquote, sees. It sees the direction and the amplitude of the magnetic field or the magnetic flux density in space at the point where there's the sensitive part of the sensor. What's going to happen as our magnet gets weaker because we can't get a hold of those nice heavy rare earth elements and sometimes even the light rare earth elements, our magnets are going to be intrinsically weaker. So the amplitude of this field is going to get smaller. And now we're going to decide, okay, what are the different factors that we can adjust so that we can compensate for that overall weaker magnetic field. And we're going to break them down into three basic categories: electrical, magnetic, and mechanical. What are the electrical changes we can make, the magnetic changes we can make, the mechanical changes we can make? Some of these are a little bit arbitrary. For example, increasing the magnet size. Is that a magnetic thing or a mechanical thing? It doesn't really matter. I kind of chose to put it under magnetic, but it's kind of a mechanical decision, right? It's just the size of the design. I'm just trying to keep things organized, but the specific category they fall under doesn't matter too much. Let's start with electrical and what happens if we change the sensor filter. Okay, so inside our sensors, and most sensors, not just NPS, have some type of filtering that goes on, especially the Hall sensors. We could actually change the window size of the filter that occurs. And what I've got here is a graph. This is our MA780. I've got here a graph that shows the magnetic field or the magnetic flux density on one axis. So how much flux density do we see at the sensitive point of the sensor? And the filter window, this is the filter window size on another axis, on the y-axis. And based on that, this is the resolution that we expect to see out of the part. So one thing that we can already see is that as the magnetic field or magnetic flux density decreases, the resolution decreases for any given filter window. If I'm at filter window 4, I've got 9.5 bits at 100 millitesla, at 55 millitesla, 9 bits, 35 millitesla, 8.5 bits. You know, you get down into 10 millitesla, 15, 10 millitesla, you're only at 7 bits. So as the magnetic field decreases, the resolution decreases as well. But we can compensate it. So if I have a lower field, let's say I have my field on my filter window 4, and I have my field from 90 to 45. Actually, that's a bad example because that's not that much of a difference. Let's go 70 to 35 at filter window 4. So 70, I've got over 9 bits to 35, and now I've got about 8.5 bits. So I'm losing a bit of resolution by doing that. Well, I can gain it back by increasing the filter window size, and I get my resolution back. So then the question is, why not just always increase the filter window to its maximum size and get the most number of bits? And that is this trade-off here. We're trading off dynamic bandwidth. Every time you increase that filter window, the dynamic bandwidth decreases. And that basically means that if we have a fast acceleration or a fast change in angular velocity, the sensor is going to lag a little bit because it's got this filter window that's still filtering in past many past points to increase the resolution. To illustrate it, we're going to actually take a look at, all right, let's take a look at MA780 with a filter window of 6 and MA780 with a filter window of 12. That actually reduces the dynamic bandwidth from 2.5 kilohertz down to 39 hertz. which is a huge difference in dynamic bandwidth. And I'm going to use we've got a online simulator tool, and we're going to be looking at that online simulator tool a lot during this presentation. But here is an example, and I've got a MA780 here with its cutoff frequency set at 2500. I can choose what I set it to, but here I've set it to 2500. I'll talk about more of these parameters later on in the presentation, so don't feel too lost here, but let's just launch a simulation. And I get a magnetic field of around 29 millitesla, 28.9 millitesla, where I've got my sensor, and that means I've got a resolution of 8.94 bits. So almost 9 bits of resolution. It's exactly what we expected, right? 29 millitesla of field, 9 bits. Let's take a look. 29 millitesla of field is here, and I've got my filter window set to 6. Hey, look at that, 9 bits. If I want to set it to 12, way up here, I should get, at 29 millitesla, I should get right around just under 12 bits of resolution. Let's check it. Again, that's just the simulator. I've got links saved. I'm using a 5 by 2.5 millimeter magnet, 5 millimeter diameter, 2.5 millimeter height magnet, MA780. Now I've got it set to 39 hertz, and I'm on axis with an air gap of 3.25 millimeters. Same as the previous simulation, so I should get the same field. I do, 28.9 millitesla, but now I've got 11.81 bits, and that's because I adjusted that filter window. So the simulator works, and it even, if I choose the right part, it even tells me how many bits of resolution I get. So that is one of the things that we can do to compensate for lower field. We can change the sensor filter window. Another thing that we can do is that we can choose a more sensitive sensor component. For instance, MA730, this is a Hall-based sensor. To MA600A, this is a TMR-based sensor. And now I've got a very similar graph to the previous one, except it's just magnetic field versus resolution for a given cutoff frequency. And we see exactly what we saw in the previous one, which is that as I reduce the magnetic field, especially when I get below 50, our Hall sensors start to drop off resolution. We could compensate that by changing the cutoff frequency, but in this case, we're not using that as a variable. So we drop off. Hey, look at MA600. This is a TMR-based sensor, and it's already got higher intrinsic resolution, and it doesn't drop off. It's very, very flat. That is an advantage of TMR. This is because Hall sensors are very white noisy. They have a lot of white noise. And it's also why filtering works so well for Hall-based sensors. Whereas TMR is mostly 1/f noise. So you get a very, very flat response over lower magnetic field. One of the things that we can do if we don't want to watch our magnetic resolution drop off with a lower magnetic field is change to a TMR-based sensor. The trade-off is cost. Hall sensors are a standard silicon process. We can throw it on the silicon with all the digital circuitry and everything else in a very standard process. TMR is not a standard process. It requires a second die, so it's always going to be a dual die solution with a specialized die for TMR, and it's expensive. Where you can get, we can basically assume that a TMR sensor is going to be 150 to 200% higher cost than a Hall-based sensor. But look what you get for your money. I am going to move to the next one. Here, another electrical thing that we can do is we can change the sensing axis. In this case, we're talking about changing. I mentioned that most of our sensors are sensitive in the plane of the sensor. This is what we call a standard mag alpha part. We also have parts that are so-called differential. They're sensitive in the orthogonal component to the plane of the IC. So here, these are all what we call planar Hall cells. They're sensitive in the Z direction. And we look at the difference of the field. You can see if I've got a magnet here, here's the gradient field created by that magnet. It's going to create a magnetic field pointing down on one side of the IC and up on the other side of the IC. So that's a differential field. That is sometimes that's going to be a more sensitive axis than the planar field. There's a trade-off here when you go to differential, and that is you can't use differential in side shaft. If I try to put the differential in side shaft, it's going to look, everything's going to be pointed in the same direction, and we're going to get no output. These types of parts you can use in side shaft. Let's take a look here real quick. The MA732, which is the standard this type in our simulator. And I'm actually going to go through from the beginning on this one. Let's start. If you go just to sensors.monolithic.power.com, you will see this page, and you can choose, do I want to look at a mag alpha sensor or a mag vector sensor? Mag vector is not an angular position sensor. It's just a dumber sensor. It just tells us, hey, it just reports the point field. It just says in the Z direction, I see 32 millitesla. In the X direction, I see 40 millitesla. Y direction, I see X millitesla. Everything that we're doing today is going to be based on mag alpha sensors that's giving us angles out. And this one, we can choose whether we're doing end of shaft, side shaft, or so-called side shaft orthogonal. We're doing end of shaft on this particular one. And what kind of magnet do we want? Cylinder with a hole, or 2 half cylinders. We'll talk about this later in the presentation, but this one's a regular cylinder. And now we can choose the remnant field of the magnet we're going to use. So we're using sintered neodymium, ferrite, plastoferrite, plastoneodymium. This one is sintered neodymium. It's 1.2 Tesla. 1.5 millimeter height, 3 millimeter diameter magnet. So that's the size of the disc magnet. What part number are we using, and what do we have its filter set to? 732 and 740 hertz. And then where does the sensor exist with respect to the magnet? So here I've got from the center of the magnet to the center of the IC, I've got 3 millimeters, which means that there's an air gap of 1.75 surface to surface. And advanced parameters, we could talk about in another webinar. We could do an entire 2 or 3 webinars on the advanced parameters. We're not going to worry about those today, but let's go down and simulate. And I get a 28.9 millitesla field at that position with that size magnet, which gives me 10.3 bits of resolution. That's with this type of sensor. If I change to a differential sensor like the MA900 with a very, very similar, we want to compare apples to apples here, so I'm keeping the same cutoff frequency. I've got the MA900 now, same thing, 3 millimeter by 1.5 millimeter height, 1.2 Tesla remnant field, 900, 776, same air gap. Let's go down and simulate it. And notice I now have 4 different magnetic fields that I can now, and when I do that, every time I forget when I do that, it's going to take me down to the definition of magnetic field because I highlighted it. But I now have 4 different sensors on this part, right? And they're each sensing 21.9 millitesla max. But actually, Z1 and Z3 are in opposite directions. So it's like having 42 millitesla, and 2 and 4 are in opposite directions. So I get the higher resolution. 11.17 bits is about, it's going to take me down there again because I highlighted it. I will never learn. It's every time I do it. So anyways, 11.17 bits, we get higher resolution because we went to differential. So another trade-off that we can make. Again, the only trade-off here is that if we use this sensor, we're on axis only. We cannot never take a differential sensor and move it off axis, whereas with this part, we can. All right, a mechanical adjustment that we can make. We can reduce the air gap. That's the simplest mechanical adjustment that we can make. So here's an MA702. This is, it will illustrate something that we can do in the simulator where instead of saying I know there's sensor position, we can scan a sensor position. So here I've got a ferrite magnet, 385 millitesla remnant field, 5 by 2.5 millimeter magnet. I've got the MA702, which has a set cutoff frequency, by the way. You can't choose anything. And I'm going to scan my air gap from 0.75 to 4.25. And I can do that. And it's going to give me the entire scan here. And you can see that if I had a neodymium, if I had a high BR magnet, I'd probably be okay with air gaps of 2.65 millimeter, maybe even 3 millimeter air gap. I'm not with a small, with a ferrite magnet. It's got the lower BR. And so I've got to reduce my air gap. If I lower my air gap, that field increases. And you can see that if I've got, about a little over a millimeter of air gap, I get into a field that's okay. This actually tells me, for the 702, we recommend at least 30 millitesla. If I have an air gap that's 1 millimeter or smaller, I'm above that 30 millitesla. So reducing the air gap is a really, really easy way to exponentially increase the magnetic field, or the magnetic flux density that we see at the sensitive part of the sensor. Another mechanical thing that we can do, and this is very specific to, so far we've talked a lot about on-axis applications. Here's an off-axis application. Something that I commonly see customers do when they're off-axis is place the sensor in a spot that has poor flux density. So let's take a look here. I've got a magnet. This is my magnet here. I'm going to use my laser pointer to make it a little easier to see. This is my magnet here. I've got a magnet that is, about 2.5, so 5 millimeter diameter and 1.5, so about 3 millimeter high, probably 2.5, 3 millimeter high. And these are the ISO lines of the flux density. So you can see that if I'm in this area on axis, or up here on axis, it's quite nice. If I'm going to be off axis, I want to be centered. I want to be axially centered on the magnet. If I get down here into what I call the corner placement, it's a very, very weak magnetic field. We're wasting a lot of the flux density that this magnet is providing because we're in an area where it just doesn't exist very well. And we're going to use a scan to illustrate that again. I'm going to scan over here with an R of about just under 2 millimeters, or R air gap under 2 millimeters, and we're going to scan from 6 millimeters up to 0 on the Z. So 6 to 0 to come up into here. And when we do that, we're going to see how much the field increases. Okay, so I've got 2.5 by 5 millimeter magnet. I'm going to use the MA78 and 710 this time. Doesn't really matter. I just chose that one arbitrarily. And I'm at a 1.5 millimeter air gap, 5.5 millimeter center to center on R. And I'm going to scan from 0 to 6, or 6 to 0, however you want to call it. But we'll call it 6 to 0. And let's do the scan. We're scanning basically along that red arrow that I showed. And you can see when I'm down in that corner, I have very, very low flux density. And as I increase I decrease my Z, essentially, I'm going towards the axial center of the magnet, the flux density gets higher and higher and higher. Now, something interesting we're seeing here. We're seeing that we've got two different magnetic fields that are being measured. That is something that's specific to being inside shaft. And our radial field is going to be different than our tangential field when we're inside shaft. Again, something that we can cover, or I have covered in other webinars and in the data sheet. This is called ellipticity, and it can be compensated by our sensors. But the important thing here is just to see that we go from low field to a significantly higher field as we move from down here up to here. Best place to be is axially centered. All right. And then something that's another relatively obvious kind of thing that we can do is we can increase magnet size. So I'm going to compare a small neodymium. So here's a 1.2 Tesla BR neodymium that's only 2.5 millimeter by 1 millimeter height. And I'm going to compare that with a ferrite that's 5 by 2.5 millimeter, about double the size, right? Well, it's more than double the size because it's volume, but double the diameter and about double the height. So let's take a look at this 2.5 by 1 millimeter magnet, neodymium 1.2, 2.5 by 1. I'm going to use the MA710 again. It's arbitrary. It doesn't matter. Also, if you're using a competitive sensor, which I certainly hope you're not, but if you are, you can still use the MPS tool. You just wouldn't choose a part number. You ignore what the part number is. The magnetic field density, the field strength, is going to be accurate regardless of what part number you choose. The part number and the cutoff frequency only is used to tell you what resolution you would get for a particular mechanical setup. So you can use other sensors and still use this tool. Here we're going to have a 2.75 center to center, 1.75 air gap. So 2.75 millimeters from the center to the center. And we run the simulation. Let's see what we get. We get 17.8 millitesla of field. for a resolution of 11.2 bits for this particular sensor. Okay, 7.8 milli. Let's remember that 17.8 millitesla with our neodymium, small neodymium magnet. We're going to increase that to a ferrite of 5 by 2.5 with the same part. Here, the way we know that we're using ferrite now is we only have a 385 millitesla remnant field. 5 by 2.5, same 2.75, and we get more magnetic field. 32 millitesla field for about the same resolution. All we did was increase the size of the magnet and use a much cheaper magnetic material, easier to get a hold of magnetic material, and the trade-off is obvious. The trade-off is it is just larger. That is the only trade-off. You actually also get an unexpected benefit when you do this, though. When you go from a smaller to a larger magnet, you can have more mechanical tolerance stack up. So let's say you've got run out on your motor, or you've got lateral play on where your sensor exists. The same amount of run out or lateral play with a larger magnet will cause a relatively less effect on INL or linearity. If you have a small magnet, a correspondingly smaller mechanical play will cause that same INL. So this, if you can do it, a larger, cheaper magnet is better. It's just, can it fit in your design? And then another thing that we can do with our magnet is we could change the magnetization orientation. So I've got two different magnets here. These are subtly different magnets. This one is diametrically magnetized, or diametrically magnetized, some people say. It means that I've got a magnetic moment that goes across the surface of the magnet like this, in this direction. That's diametral. That's a typical magnet that we use for a typical magnet that we would use for target magnet. This one is called a biaxial magnet, or it's essentially two hemispheres of magnet. The magnetic moment is down on the left side and up on the right side. It's still going to create this kind of field that circles around here. You can still use this for an on-axis sensor. It's very nice. Let's take a look at the difference when we use a diametral magnet versus a biaxial. So this was diametral. We're using a ferrite magnet, size of 3 millimeter diameter, 2 millimeter height. We're using the MA782, again, arbitrarily chosen for this one, and a 2 millimeter center to center, so air gap of 0.680. We're going to run the simulation, and I get 32.7 millitesla of field. By the way, how do I know what magnet I chose? Well, I would know it normally because I choose the magnet back over here. I would choose in the shaft, and I would choose this cylinder magnet instead of this 2.5 cylinder. But in case I forget when I do my simulation, I can always go to this report tab over here. And you go to the report, and this tells me, oh, it's a cylinder magnet. Okay. And the cylinder magnet means diametral magnetization. So we're into shaft, cylinder, 3.85 Tesla, 39 hertz cutoff frequency. It tells me everything I need to know about my application here. 32.7 is my magnetic flux density at the sensitive part. This report also shows me a URL that I can use to get back here. This is what I've been using this whole time. These URLs, I can copy it, and then I put those in my presentation, and that's what I use. Here's one that does the same design, but with the biaxial. So it's the same exact design, 0.38523, 782, 0.680 air gap. I'm gonna run the simulation. I get higher field, 40.3 millitesla. And the way that we know that this was biaxial is if I go to the report, it says half cylinders axially opposed. So higher field because of the biaxial. What's interesting with biaxial magnets is you'll get a higher field when you're close, and as you go farther away, the field dies off faster than it does with a diametrically magnetized magnet. So these are commonly used not just to get higher field strength at for a very close sensor. It's also used commonly if you've got multiple axes and you want to put a bunch of these rotating magnets where, maybe you have a bunch of motor shafts that are all close together and they all want to have sensors, and you don't want axis to axis to interfere with each other. Use a biaxial magnetization. The field drops off very, very quickly, and it won't interfere with a nearby sensor magnet setup. All right, and lastly is we can change the number of poles. And unfortunately, I have to go through this one really, really quickly because I'm running out of time. But we change the number of poles. We can change from 2 poles to 4 poles to 8 poles. The trade-off here is that you lose absolute angle detection. If I have a dipole magnet, I can turn off my device, rotate the magnet to any arbitrary position, turn the device back on, and I know exactly where I'm at because the field has a 1-to-1 match with the angular rotation. If I go to a multi-pole magnet, for instance, here's a two pole pair magnet. If I rotate this one mechanical rotation, I'm going to see 2 full magnetic rotations. And if I turn it off, rotate to an arbitrary position and turn it back on, I don't know which pole pair I'm seeing. So I lose my absolute angle detection. What I gain is, when I'm really close, higher field because I get the flux densities concentrated over only 180 degrees as opposed to 360. But also, I doubled my pole pairs. I get an extra bit of resolution for free. So I go from 1 to 2, I get an extra bit of resolution. I go from 2 to 4, I get another extra bit of resolution. I'd have to go to 8 pole pairs to get another bit. And pretty soon, this becomes a problem because I have to have the gap between, by the way, you only do this on side shaft. If I put a sensor on here on axis, it wouldn't see anything because this is all axially symmetric. This one is the only one that's not. So this has to be side shaft, and I need to be close enough that the distance from the sensitive part of the sensor to the magnet is smaller than the pole pitch, because otherwise these poles will start to cancel each other out as I move farther and farther away from the magnet. And so that's when you're trying to pack 8 pole pairs into a small magnet, you have to be so close that the package almost has to be touching the magnet. So there is a limit to how many times you can double the number of pole pairs. But extra pole pairs increases the field and gets you that extra bit of resolution for the weaker, say, ferrite over neodymium. And it's much, much easier to make a ferrite magnet with multiple pole pairs than it is neodymium. Okay, so just a quick compensation review. 2 main things that I want everybody to remember. There's a lot of switches and a lot of things that we can play with, but 2 main things I want people to remember. In general, because we can't get a hold of these rare earth elements, or they're difficult to get a hold of, we're going to be using magnets that have a lower intrinsic field strength. When we do that, that means that our resolution is going to go down, but we can compensate it. So the gray is what we're dealt, the hand we're dealt. How we compensate is in blue. What we're going to do is we're going to lower the dynamic bandwidth, which increases the resolution. That compensates for that lower field strength. Same thing, magnetic remnants, which is what causes the lower field strength. When we have a magnet that has a lower magnetic remnants, I want to keep the field strength at the sensor the same. I need to increase the magnet size or decrease the air gap. These are the 2 most important things that we can do to immediately compensate, and then we move on to all these other different, so electrical, more sensitive sensor component, change in the sensor filter, finding a sensitive axis with a higher flux density, smaller air gap, moving to an area of higher flux density, and again, use that sensor simulation software to play with it and see what happens. You can watch this stuff in action as you scan across different zones, or you do different, run different simulations, increasing magnet size, changing the magnetization orientation, changing the number of pole pairs. The simulation software is at sensors.monolithicpower.com. You can always contact me, and I love teaching people how to use it, and I've got some intuition built up for you. I mean, it's something I use literally every day in my job. With that, I will take some questions if we have any.
Thank you, Ted. Great presentation. So quick reminder for everyone, you can scroll over to the bottom of your Zoom window. You will see the Q&A button. So please type in any questions that you might have. Right now, we'll give people a few seconds for more questions to come in. Brian, feel free to start with the first question.
Okay. Thanks, Ted, for the presentation. I thought that was very good. One question is, what sensor technologies are used in these position sensors, and what are some of the advantages to each technology?
Yeah, so the vast majority of MPS sensors, at least, is Hall. And the advantage for Hall is clear. It's a very well-known technology. It's inexpensive because it's a standard silicon process, and you can build it in the three axes. We can do planar Hall cells. We can do vertical Hall cells. So it's very flexible. We also have some parts, and I mentioned this, the MA600, for example, that are TMR based. And the big advantage to the TMR is the higher sensitivity, the fact that you get the intrinsically higher resolution. It is this one. You get the intrinsically higher resolution for the same magnetic field. The trade-off is cost, but this higher resolution, higher sensitivity, it's got some other advantages as well that are a little more subtle. But this is the big one, not the extra resolution that you get for a given field. There are other technologies out there. Most of them are magnetoresistive based technologies, AMR, GMR, and I think that, well, I may be biased because I'm an MPS, but I think that MPS has got the two right ones. I mean, there's some that fit somewhere in between here, but I think Hall is very, very flexible. TMR is very, very accurate. And I think those are the two technologies that I would focus on, even if I were looking at an arbitrary sensor.
Okay. Next question. If you can't change the sensor, air gap, or magnet size, can you speak to some simulations you've done with whole pieces or yokes?
Yeah. So the simulation software that I showed, the MPS simulation software. Can I get it here? I'll just click on it, get it. Has some limitation where we're doing the 90-10 rule, where we're trying to cover 90% of the applications. Come on. And so if I go to the beginning of this tool, you'll see that I'm limited with this tool in. Let me go to side shaft. These are the magnets that I can choose, and they're all ring or disc based magnets. The place where pull pieces come in, and I'm assuming that you're talking about not multiple pull pieces that are put together into a disc, but actually having just a wedge or something like that. If you don't have a 360 degree full movement, if your range of motion is only limited, then you can use just a pull piece. I can run that simulation for you. The Python code that this is based on, I have access to, and I can run simulations that are outside the bounds of what the online simulator can do. The online simulator is limited to disk and rings. But certainly we can run simulations like that, and we do for customers all the time.
Next question. If you were to place a sensor in the middle of a ring magnet, is there a way to simulate the position of that in an application such as a scroll wheel?
Yeah. So let's do that. I'm going to choose sensor location. I'm going to choose side shaft, even though it's not really side shaft. You're talking about placing it inside the ring. That's okay. We're going to go side shaft anyways because it gives us more degrees of freedom to place the sensor. We're going to go sensor with a hole, and I'm going to take. This is obviously arbitrary. What happened to come up, but a 5 millimeter by 2.5 millimeter height, 3 millimeter ID. And to place the sensor in here, what I'm going to do is I want the sensor to be inside this hole. So that means I want the R to be 0, and I want Z to be 0. In other words, I'm going to place the center of the sensor in the center of the magnet. And I can do that. I just say R equals 0, Z equals 0. And for this particular one, I get a lot of field because I'm inside that ring. And there you go. You can see it works actually quite well. But yeah, you can choose your magnet ring size, your magnetic material, and play with this. But it works very, very well to put a sensor right inside that a ring.
Next question. So you didn't address clean earth or green magnetic technology, such as Niron magnetics, which uses iron nitride.
Yeah.
Can you talk a little bit about that technology, how it compares to, say, for instance, samarium cobalt? And is there a way to simulate that in the simulator?
Yeah, for sure. So we can simulate it in the simulator, definitely. The problem with so this is exciting. I hope it's exciting technology. There's permanent magnets, no rare earths, made right here in the United States in Minnesota. There's a couple of these companies I've seen. They call them green magnet companies. They say they've got high performance, rare earth free. You could simulate these. All we need to know is what's the BR, and for temperature, maybe the coercivity, but really you just need to know the BR. The problem that we have is if we look here, I don't find any data sheets or actual product. So I love the idea of these. I'm excited for the day when I can actually see a data sheet. So I'm hoping that this is real and that this is that they'll have something soon, but I got to see a data sheet. I need to see what the actual characteristics of these magnets are. The idea is great and I'm super excited, but I hope it's not the nuclear fusion of the magnetics world.
Okay. Apart from Niron, are there any other companies outside of China that manufacture heavy rare earth magnets?
Basically, no. I mean, there are companies outside of China. I shouldn't say no. There are companies outside of China that manufacture magnets that use rare earths, but they get, almost without exception, they get their rare earths from China, or they used to. It is Dexter Magnetics, Arnold Magnetics. Those are both here in the United States. Bomatech is in Switzerland. As far as I know, they do their manufacturing in China. I've got a list from those guys, and I didn't go into what's available now and what's not available now because it changes weekly, let alone, by the month or the year as you're trying to get into your design. But in general, right now, what you can get from those companies that source out of China but aren't built in China is about N40 to N45 SH. Nothing higher than that. You can't get an N48 SH, and that's the current state. And then even with the non-heavy rare earth, it becomes sometimes difficult to get just the standard neodymium. You can apply for an export license, and then sometimes shipments get delayed because they do inspections. This is kind of, in terms of what I'm willing to commit to, and this is about as good, as specific as I can get, because like I said, it changes. So right now it's ferrite is no problem. You can get it, absolutely no problem. When I made this slide, I said no problem to get bonded neodymium. That's still for the most part true. There's enough stock out there. I have heard a couple stories, but I have nothing verified, where there's been things that have gotten caught up and delayed. Simcoe is almost impossible to get a hold of right now, and sintered neodymium with grade above N45 SH is almost impossible to get a hold of right now. I think that there are certainly companies that are all kinds of startups that are, or I don't even know if they're startups, but companies that are getting into the rare earth business because there's an opportunity out there. But man, that kind of supply chain and that kind of capitalization is not something that's going to happen in 1 or even 2 years. I think that's going to take a half a decade before we really start to see any major alternative to China. That's why I'm really rooting for these green guys like Neuron, but they've also been around for a long time, and I haven't seen a data sheet. So it's kind of, let's see.
Okay, another question here regarding the simulation software. Is this finite element or analytical?
Simulation software that's online is analytical. We can do finite element analysis on a kind of case-by-case basis. The problem with finite element is that it's so specific to what you've got in your design, and so we would have to talk to somebody to do it. That software that we have requires a license, so we would talk to you. It's really only useful. FEA is only useful if you've got soft magnetic material in the vicinity, or there's some kind of like eddy currents or something, some kind of dynamically changing magnetic field. Then we can do finite element analysis. But the simulation that's online is analytical, accurate to within a few percent, couple percent, let's say.
Okay.
All right. If that's all the questions, thanks everybody. I appreciate you sticking around and listening, and reach out anytime if you have questions regarding how to change your design or how to utilize the simulation tool.
Yep. Thank you, Ty. Thank you, Brian. We'll be sharing the presentation and the recording plus the simulation tool in the next few days, so you can receive it and use it for your convenience. So if you're interested in more webinars like this, feel free to check out our website, monolithicpower.com/support/webinars. So stay tuned for future webinars. We have plenty of interesting topics coming up. Thank you, everyone. Hope you have a great day.